So my project is the Smart Tab Predictor, which is a Chrome extension to basically help manage your tabs and automate a part of everyone's daily life, essentially. So some keywords for this are just machine learning, Chrome extension, and task management. As the main goal of this extension was to help automate daily web browsing. So some problems I had during the COVID lockdown with online schooling was repeatedly going to the same URL over and over again, such as Google Classroom or Schoology, at like the same times every day because school is always on the same set schedule. So this could sometimes result in me opening too many tabs and then having to find the right tab that the teacher wanted us to be on. And then sometimes if I had too many tabs open, the browser may crash. And it basically just makes it so that I would easily lose track of all the different tabs I was on. So then this led me to think if there was some way that I can just automatically help me open all these different things at these set times for the specific classrooms, such as AP Chemistry, like early in the morning at like 8:30. So so the goal of the project was to provide like something that gives a suggestion of a URL similar to the auto browser feature or the autofill feature on the browser. Like if you type in GO, it'll automatically fill to Google, but instead of automatically filling the current website you're trying to go to, it'll fill in the next website you're trying to go to after you go to a certain website. Essentially, this will just improve user productivity with fewer clicks and just automate a part of web browsing. So some challenges I had with creating this program was selecting the proper machine learning algorithm to consistently return the correct result. There were certain machine learning algorithms that were better suited to the challenge rather than others. For example, I used the Python machine learning algorithms such as SVM, hidden forest classifier, and random forest classifier. The main one I chose out of those three was the hidden forest classifier, as that one worked the best with the data set that I was using. I determined the prediction accuracies with another built-in feature of those machine algorithms, basically something called cross-validation, which essentially returns the accuracy of the different types of predictions. And then, so with this machine learning algorithm prediction, I had to tailor it to each specific user that wanted to use the program. So essentially, I had to find a database to store all the URLs of a user. I had to store the time, date when they open the website, and then I also had to just pull from the database and push things into it. And since this was my first time, that was the big general challenge, and I had to find one of those things. And the database also had to be strong enough to the point where it can hold all of these large data sets, because the data sets will be the browsing of your everyday person, which can vary from high numbers. And the data sets needed to be modified based on what the user is going to. So this is the solution that came up with. So we start at a Chrome extension over here with just at the top, the green person with the Chrome extension, and then the Chrome extension is made with JavaScript. And on opening a new tab or going to a new website, the Chrome extension will run a Chrome API, which will essentially just get the time and date and the URL that the user has opened, and then it'll send it into the Firebase Cloud Firestore, which is the database that I decided to use for this project. Afterward, then the machine learning algorithm will take the data from the Firestore or Firebase, and then it will send it. It will take all the data from the Firestore or Firebase, and then it'll check which URLs are closest to one another in a certain time frame, which I'll talk about later. And then after that, it'll return a result in through the web server Flask, which basically is like a website that runs a certain algorithm, and then that'll return the result back to the Chrome extension. And then in turn, that Chrome extension will return the result of the new URL to the Chrome browser user in a little pop-up in the top right. So here is the Chrome extension user interface. So as you can see here, we have a login screen. So this was done just using HTML and CSS. And Firebase actually has its own user password type of interface. So I just used the documentation from there in order to get this interface set up. So we have a login, sign up, and sign out feature. So, and then on the bottom here, you can see a next URL and then recommended site. So basically, once the user goes to another website, there will be something that pops up under the next URL, such as like, say you go to Google, then the quote unquote recommended URL would be Google Classroom, and then it'll show up. And then if you hit the highlighted section light blue, or the recommend site, it will take you to Google Classroom. And then underneath that, you can see the different types of test emails that I created to see if the databases will work, and basically just testing around to make sure that there were not bugs. So the different components inside the Chrome extension were the pop-up scripts. And so the pop-up scripts were used to handle the user logins and the signups and signouts. So essentially those were taken from the documentation of the Firebase, the built-in Firebase user system. And then it essentially sends a quote-unquote handshake request to the background scripts, which basically is just the backend for the Firebase. And then the backend scripts initialize the connection to the Firestore database, which is what stores all the different information we have. Essentially, it stores the email of the user that is currently logged in, and it stores the year, month, minute, and second, hour, minute, second that the user goes into the website with. And then it'll listen for the events such as the user opening a new website. And then once the website is open, it'll send the information from the prediction back to the pop-up on the JavaScript, and then which in turn will essentially return the results of the prediction. So here's the backend for the Firebase. Right here, currently, this is unencrypted, but later on I added hash 512 encryption for the emails. But for now, this is really just for more visual effect. As you can see, we have just one section for all the data, and then in the subsection we have the different emails that the user is logged into at a time. So as you can see, we have 3 different ones. We have temp email, test email 2, and then test email. And then with in all of these 3 different accounts, they have their own set of URLs that they all been to at a time. So this will basically allow the Firebase to categorize every different user with their own unique set of URLs, allowing for better predictions, and so that each user has their own special tailored machine learning algorithm, essentially. So in order to access the Firebase, as mentioned earlier, we use the Flask server from Python, which are basically, so I can see here we have the app route, which starts with / take input output, and then with all these little brackets with month, day, hour, minute, URL, and email. This is essentially creating a URL that when ran will run the machine learning algorithm function. And then once the function is done, it'll return I make it return the URL that it gets back to the website that the thing is on. So if I actually type in repl.data / take input output with a bunch of random numbers, and then I give a valid email that has data in it, it would return some URL that the prediction returns, that the prediction would give. And this is the machine learning algorithm itself. So this was all hosted on the REPL platform, which is basically just online IDE. So from the start, we encode the dataset from Firebase to the format that the machine learning classifiers can read, calling one of the machine learning classifiers from the sklearn libraries to perform the prediction. Then it decodes the predicted result to a human readable format So you can see that here, we turn it into a pd.data frame, so which basically just separates everything, and then we run that through the machine learning model. And then afterward, down here, we can see the final result with the output encoder, where we transform it back into a human readable format, and then we can see the final result, and then we return the final result to the website done from the Flask server. So here is like the more of the core of the Flask web server. So essentially, this is just this is everything that is used in order to get the result back to the extension. We have to use all these different types of imports with and importing Firebase, and just essentially just more backend. So here are the experiments from the 3 different types of machine learning algorithms I decided to use. So as you can see, we have the SVM machine learning algorithm in blue, and passive aggressive in red, and random forest in yellow. As you can see, the cross-validation score for the random forest classifier is exceedingly higher than both the passive aggressive and the SVM machine learning model. This is because of the way that it actually performs this machine learning algorithm. I can go more in depth later if you have questions on that. But for now, this cross-validation splits at the bottom represents the amount of times basically that the algorithm will check over the results that it returns. So CV3 will make sure it checks like less per se, and that's why slowly as time goes on, as you can see with CV3, CV5, and CV7, the random forest accuracies just get higher and higher because it proceeds to check more, and then it's validating itself even more. So essentially, SMOTE. When experimenting, we had to apply SMOTE in order to offset the no tab prediction, since most of the time people do not constantly open tabs one after another. They might sit on there for a set amount of time, which might exceed the time limit that I have set inside the machine learning algorithm to take the URLs in. So in order to counteract that and to get a no tab prediction, we apply SMOTE, or a synthetic minority oversampling technique, which essentially balances the data sets by increasing the minority class examples. So basically what this means is, say that we have a bunch of the URLs inside a database, but all those URLs are open at different times. So the tab predictor will print nothing, but the tab predictor will predict nothing if you run a URL. But say that, but since there's so many results that say, oh, there's no tab after this because it's happened so many times, this will counteract that and give you a correct prediction, as it'll just fill up the machine learning algorithm with duplicates of the different types of URLs. As you can see here in the cross validations, as time went on, with all these different post-SMOTE, after we applied SMOTE into the machine learning algorithm, the accuracy is like nearing 100, as SMOTE will help counteract that no tab prediction, which is causing that small inaccuracy. The feature importance is essentially calculating how important each feature of the tabs I need. So for example, I take the month, day, hour, minute, and second whenever a user opens a URL. As you can see, the month has 0 average feature importance score, as most of these predictions were done in the same month, thus resulting in the month always being the same. And then the days, it just slowly goes on, and you can clearly see that the second is clearly the most important part, as it is the most constantly changed variable in time. So we had to experiment in order to find the best time interval for our predictions. So we tested with 30 seconds, 1 minute, 2 minutes, 5 minutes, and 10 minutes. And then we decided to go with a 2-minute interval, as it is the most relatively realistic amount of time between opening consistent tabs, as the teacher might be talking, or you might want to take a drink of water or something. 2-minute intervals seem to be the best choice between 5 minute, 1 minute, and 30 seconds. And then the months and days are used for checking the consistency between the predicted URLs, as we don't want to do a prediction with the same 2 minute interval, but then realize that the month and day are completely off from one another. And then the milliseconds are used to ensure that two URLs are not open within the same second, as sometimes people do like to open tabs that quickly. So in conclusion, I created a Chrome extension using JavaScript and the Chrome API in order to store tab history, I guess, into a database. And then through the Chrome extension, I use a machine learning algorithm that would use a Python flash server to return the result back to the Chrome extension. And that would help predict the next future tab that someone would open, resulting in a more automated workspace, just causing more productivity and less stress. And yeah, any questions?